Thank you very much. Again, following Czaslaw, and now for something completely different. So we are going to tour the world of experimental physics, and I would like to address the question whether it is feasible to think about sources of gravity in superpositions from an experimental point of view. So can we go beyond thought experiments? The story is well known, so I will, exactly. So, and basically, this is what we are driven by, because the overall opinion over the last 60 years has essentially been that there's no way that we can be pushed by experiments in this field, so we rather be pulled by imagination. So let me pull your imagination and push you towards experiments, okay? So this is now the aim of this talk. So the story is a well-known one. I will do that quickly. It starts with the statement that today all experiments that we have at the interface between quantum physics and gravity can be explained by assuming the validity, number one, of quantum theory, and in combination with the validity of our current theory of gravity, namely GR. So in the best case, the experiments that we have can be described by a, let's say, quantum field theory in curved spacetime, but that's it. And all those experiments are very beautiful. I don't go into the details now because time is short, but definitely, so what you see here is experiments where the wave packet of a neutron is influenced by Earth's gravitational field in a neutron interferometer. This is the famous cow experiment by Colella, Oberhauser, and Werner. And here, a gravitational redshift experiment where by raising an apparatus in the lab, an optical clock in that case, you see the frequency of the optical clock shift in Earth's gravitational field. So all of that are beautiful demonstrations how quantum systems are extremely sensitive to classical external gravitational influences. However, the question remains whether we can have phenomena which a classical theory of gravity is unable to explain. This is the question we would like to address. So first answers to that were given back then. This is actually the quote that I had on my title slide. This was also from Feynman at this famous Chapel Hill conference. And the positive answer that was given back at the conference in the discussions was that yes, in principle, if we think of a experiment where we produce one gravitational source mass in a superposition of distinct center of mass states, that are in principle distinguishable as that are distinguishable with respect to their gravitational influence. However, in a quantum superposition, then by adding a test mass in the vicinity, we can generate quantum entanglement via this gravitational interaction, which is inconsistent with the very assumption of classical GR, namely that each source mass configuration results in a fixed spacetime geometry within which my test bodies fall along geodesics, and hence I would never be able to generate entanglement. So this is the story. The story essentially concludes with a question that Louis Witten asked, namely also at the conference to Feynman, what prevents this from becoming a practical experiment? And this is what I would like to discuss now. There are essentially two possibilities, two, let's say, special cases of possible experiments that you can perform in order to generate entanglement via gravitational interaction. You could start simply by having two particles into Gaussian quantum states. So as you have two quantum harmonic oscillators separated by a distance d, and just let them interact via a gravitational interaction. Then you have a 1 over r interaction between the two. If you Taylor expand that, the first non-trivial coupling that you get is an XX interaction. So you have two harmonic oscillators coupled via an XX interaction. In quantum optics, we call it a two-mode squeezing operation that generates EPR entanglement between position and momenta of the two particles. So this is one way to do it. The other way to do it is you start with two masses in a superposition of distinct center of mass states that are initially separable. Again, the distance between the two is d, and now you let them interact with each other. What you have then is a variant of the cow experiment we saw before, namely each mass here evolves in the gravitational potential of the mass there. You get dynamical phases that evolve depending on the position of the other mass here, which eventually results in an entanglement between the two initially separable qubit states, if you want. So from a quantum information perspective, this one realizes a conditional phase gate, and once the phase is -1, you have a control qubit and a target qubit. If they both start out in a superposition, you generate entanglement. Interestingly, even though this seems like two very different experimental situations, if you ask the question, what is the rate at which you generate entanglement through gravitational interactions, where you define delta x in the Gaussian case as the delocalization of your wave packets of the two quantum harmonic oscillator states, and here delta x as the separation of the center of mass states in your non-Gaussian superposition, then it turns out that the rate at which you entangle is essentially the same in those two cases. So, which means now it's rather more a practical question than a dogmatic question, because both approaches yield the same. So now it's up to us to choose what would be the better experimental configuration. Obviously, the challenge now from the experimental point of view is how can you make the rate at which you entangle larger than the coherence rates in your system. Just to give you a feeling for the numbers we are talking about. If I take two atoms, I separate two atoms by a micrometer, let's say. So typical wave packet sizes of atoms is in the order of a few hundred nanometers, then it would take 10 to the 24 seconds for the two atoms to become entangled just via gravitational interaction, assuming that we manage to shield all other non-gravitational forces, which is like 10 to the 6 times larger than the lifetime of our current visible universe. So obviously we need to change something. So let's change the mass of the thing. So if we take two lead spheres, approximately 50 micron in size, so there's approximately a Planck mass, there are two Planck mass objects, and we separated them by 100 micron in the center of mass, obviously, because, well, they are 50 microns in size, so this is the minimum separation you can have. Then you see we are down below a second at the time it takes. So this already shows you where to go. What you have to do is you have to take large objects, and you need to make sure that you can prepare large objects in quantum states of motion in order to generate gravitational sources in quantum states. Okay, let's just rewrite this quickly. Instead of the decoherence rate, we now talk about coherence time. It's just 1 over this thing in an experiment. Then we can rewrite this expression into the following condition. So we now have these two masses that we want to entangle via gravitational interaction. D is the distance of this between the center of mass. D naught is the surface distance. I come to that, why this is experimentally important. And then our expression now boils down to this very simple, our condition boils down to this very simple expression, namely that the mass squared, the delocalization square, times the decoherence time, and times 1 over the distance cubed between the two masses needs to be larger than Planck's constant over Newton's constant. If you want to generate entanglement via gravitational interaction, that is the minimum requirement that you have for those approaches. The nice thing about that expression is you can separate it now. You can separate it into a part that you can test in independent quantum experiments. So now, one part in your lab should start building quantum experiments where you maximize mass, delocalization, and the square root of coherence time. Yeah, so the product of that three numbers. This is something you have to maximize. And you have to, so you close the door after 10 years, you open it, and the task was maximize this number, and then you need to see where you are. In independent experiments, you need to do gravity tests in which you minimize the distance between two masses such that gravitational interactions are the dominant ones. This is the actual challenge because once you start bringing those two masses together, non-gravitational interactions will start to dominate. So this is the next task. So in the end, you need to do quantum experiments where you maximize mass and delocalization with large coherence time, and you need to do gravity experiments where, using small masses, you minimize the distance in order to maximize the coupling and hence the entanglement rate. Okay? So here are three boundary conditions that you need to consider. And these are more on the experimental side. I apologize for that, but essentially this is sort of, we need to decrease the possible parameter space in which we start designing experiments in. So here's one consideration. This is something that is well known now ever since the big studies and experimental big achievements of the gravitational wave community, namely seismic noise. Seismic noise is something very dramatic. And so the point is everything shakes all the time. Okay? And the problem that we have in our experiments is that we have large masses. So think about a harmonically trapped object cooled to the quantum ground state in its trap. So we're talking about a quantum harmonic oscillator, and you ask the question, what is the wave packet size? So my ground state extension of my harmonically trapped particle. You go into an atomic physics lab, you ask the person, oh, you have a rubidium atom trapped, what is the size of your atom? What's the wave packet size? Oh, it's 100 nanometer, no? Because I have a trap frequency of a megahertz, I have a mass of one atom, and if you then just compute the ground state extension, 100 nanometer. The lab, due to seismic vibrations of this person, actually shakes all the time, okay? It shakes by, let's say, a few picometer. Okay, which is just a fraction of a nanometer. So he doesn't care. So now you try to do the same thing for not one atom, but a mass, our 50 micron mass from before, let's say. You have like now 10 to the 10 atoms. And you ask, what is the ground state wave packet size of an object trapped in the same trap, but now with 10 to the 10 atoms, where it's 5 orders of magnitude smaller. So instead of 100 nanometers, suddenly we have a few picometer wave packet size. So if now my lab shakes the same amount, again the few picometer, all hell breaks loose. Because suddenly I see the shaking in my quantum experiment, which I didn't before. So the same amount of shaking actually has a bigger influence when I do a quantum experiment with a more massive particle. So that means I somehow need to take care of that, and I know how my shaking actually decreases with increasing frequency. So the shorter I average in my experiments, the less dramatic is the influence. So what I need to do is I need to confine my duration of the experiment. So what I do is, by principle now, I demand that my experiment does not take longer than 10 milliseconds. This pushes me into a frequency regime where the seismic noise is, well, much less worse than the 1 second regime. Okay, it's still bad, but it's more manageable. So this is number one. So it means now, you see, I confine my coherence time. That's the first condition. So I do a fast experiment. Definitely helps. Second thing is, how do I isolate gravity in my gravity experiments? Because I know there's always non-gravitational forces. If I have two masses and I want them to see interacting via gravity, each and every gravity experiment has Faraday shields. So you have a very well-conducting plate here between the two masses, such that any charge configuration here creates mirror charges, which means that any position-dependent electromagnetic coupling between the two masses is nullified. I generate a coupling now between the shield and the mass, but there's no position dependence anymore. I just generate the so-called DC bias field, electromagnetic one, that I can work with in my experiment, but I don't get any position-dependent coupling between the two masses. So the question is, how well can I do that? And if I look in the literature, the best experiments today, best meaning what is the smallest distance between the two masses that I can achieve and still guarantee experimentally that gravity is the dominating interaction, is 50 micrometer. That's the smallest distance. These were Eric Edelberger's experiment at the University of Washington in Seattle. This is the current world record. So, and what they did was essentially, here for their Faraday shield, they had an aluminum coated membrane. It was like 10 micron in size, and this served as their shield. What we want to do is, we want to push that to 10 micrometer. So we think we are currently collaborating with Eric Edelberger on an experiment where we try to push the distance down to 10 micrometer between the two masses, and we think that this is a number we can work with. We think it's not realistic to go even below, but we will see. Time will tell, but this is now the second assumption that we do. You need a Faraday shield, and you will not be able to go smaller than 10 micron between surfaces. Which brings me to the last condition. This is a decoherence condition. So now we have a Faraday shield, and we have some delocalized particles, some delocalized mass hovering above the Faraday shield. Okay? So the problem is, well, there will be some interaction now. So if there are any losses, if the mirror charges you generate here somehow dissipate, you generate an imprint, you localize essentially your charges, or your charge configuration. So that means you have decoherence. Question is, what should you do about decoherence? Well, so let's say 0th order, you assume, I think it's safe to assume that the decoherence in such a configuration scales somehow to some order with the delocalization over the distance. You can make some dipole arguments and so on, but somehow this is a safe first order assumption. You get decoherence with some order of delta x over d, which now, which means you want to get that number, the ratio between delocalization and distance, very, very small. So you cannot delocalize arbitrarily large and still have small distances. There is a trade-off. Once you fix the distance, there's a maximum delocalization you can afford before decoherence kills you. So that's another constraint now on delta x and d. And you see, the only thing, now we have all three conditions together, the only thing we have not constrained yet is the mass. So we have now put experimental bounds on delta x, on a delocalization, on coherence time, and the distance. If you put all of this together, you get a bound on the mass. Namely, the mass has to be larger than this expression, which is the Planck mass times this parameter here. And this is on the order of 10 to the minus 6, the Planck mass. If the mass is too small, you would have to delocalize too large, and then you would decohere due to the presence of the Faraday shield. And if the mass is too large, well, you can always make the mass large. Yeah? So you get a lower limit on the mass. The mass needs to be at least 10 to the minus 6 times the Planck mass. Planck mass is 10 to the 18 atoms, so you need at least 10 to the 12 atoms in an object in a sort of quantum state of motion delocalized sufficiently. Okay? That is a very firm lower bound. Well, then you just believe me when I say now you basically have to need to take into account all decoherence, sources of decoherence. So you need gas collisions, you need black body radiation, you can go further, you get fluctuations of the trap, you get fluctuations of the trap frequency, the trap position, there might be some residual thermal coupling. So there's a lot of decoherence stuff you eventually will need to take into account, but I can tell you from experience, the most important point, we need to measure these numbers experimentally. So this is actually something that is very important, that we basically determine experimentally what is our noise sources in the experiment, and from that then optimize the rest. So this is my summary from what I have said now. Namely, what I put. Remember, this is what we want. We have two masses separated by a surface distance d naught with a Faraday shield. Okay? We want to have a measurement time of our experiment not more than 10 milliseconds. And we want to have a distance, surface distance, on the order of 10 micron. Typical densities of masses that we can assume in the lab is on the order of 10 to the 4 kilogram per cubic meter. This puts us somewhere between dielectrics and superconductors. Okay? So a very dense dielectric has that, a very light superconductor has that. So this is a reasonable density to assume. If I put all of that together now, then I prepared a table here. So what you see is the mass in units of the Planck mass. So if I have, let's say, if I have an object the size of the Planck mass, then I would have to have a delocalization of 1 nanometer, 1.5 nanometer, okay, of the center of mass degree of freedom. With temperatures, environment and particle temperatures on the order of 10 Kelvin in order to get entanglement on a 10 millisecond timescale. Okay? If 80 micrometer is too large for me, this is now an experimental question, can I really quantum control an 80 micrometer mass? Who knows? Well, let's go to 10 to the minus 4 times the Planck mass. I have a 10 to the minus 4 times Planck mass object, then I would have to localize 500 nanometer with, again, temperatures on the order of 10 Kelvin for the particle temperature and the environment temperature. Okay? All of that assumes now that my coherence time is on the order of 10 milliseconds. For a 4 micron object, that means that my pressure that I need, my environment pressure, needs to be on the order of 10 to the minus 15 millibar or so. Which doesn't tell you anything, but it's many orders of magnitude better pressure than we have today in our lab. So right now, the best pressures in the world that exist in 3 laboratories is on the order of 10 to the minus 19 millibar. But that is a huge effort because you have to have cryogenic vacuum chambers and so on and so on. And this is an effort that we will likely have to go because the larger the mass, the larger is the cross-section for a molecule to hit off from and localize it. So pressure is actually one of our biggest experimental issues. So, how much time? We are done, huh? More or less. Okay, so then let me give you 2 quick lab impressions, because now the question is, where are we? Where do we stand? Okay? So I told you we are doing both gravity experiments and quantum experiments. So the gravity experiments that we are doing is essentially Cavendish type experiments. So you have a mass that sits on a pendulum, you bring a second mass very close, and you measure the rotation of this pendulum here due to gravitational acceleration. Okay? This is data, just raw data from the pendulum without any gravitational interaction, and you see it's very structured. And the reason why this data is very structured is because this pendulum, if you have it here in the lab, sees the traffic light cycle of the road crossing Nussdorfer Straße, Währinger Straße. It sees the fact that there are more people on the street Friday and Saturday nights instead of not on the street the other nights, all that stuff. So basically we see night buses coming and going during the night, all these things. I mean, eventually we managed in our experiment to measure gravity between those 2 masses. You see the mass is here actually a gold mass, a millimeter in size. So we managed to actually see a gravitational signal. However, for a lab here in the city, this is the smallest you can do. Okay, so this is a 1 millimeter size source mass. Now the next step, what we are doing is we want to go smaller and smaller. So here our next experiment that we're planning is actually have this as the source mass compared to our current mass. So Hans is standing back there. So Hans is building this experiment right now. Actually not in our lab anymore, but here in the tunnel. So we have an underground lab, and this is Hans. And we have an underground lab where we are currently setting up the experiment, and where we basically using masses now of that size. And so The next step in our case right now is to really measure gravitational fields of a Planck mass object. From the quantum side, what we have been doing is we have started to work on combining solid state devices, solid state because you can cram a lot of atoms in a small volume, with the ideas of free-falling matter waves. And what we are doing is essentially we take solid objects and trap them in external traps. So for example, in optical traps or magnetic traps. So you can do that in the lab. You can actually take a microscope objective, you can focus light, you can trap a nanoparticle. This is now an object of 10 to the 9 atoms with a radius of 70 nanometers. You can trap that at room temperature, and then you can build a Heisenberg microscope. So basically what that means is you have some complex apparatus where you measure the scattered light that comes back from the object in such a way that the imprecision back action product of your measurement is bounded essentially by Planck's constant, which means that you don't lose any information. The only information loss you have is fundamentally quantum noise, which means you can now use your measurement information. You can use it to reconstruct in real time the phase space of your particle. So basically you can follow the quantum trajectory of the particle at room temperature, and you can even stabilize. So you can feedback cool now, or you can feedback on the particle to stabilize the position in phase space with a precision given by the ground state size. So we can cool now the particle to its quantum ground state of motion in phase space just by looking in it and feeding back the information that we get. And so right now this is really a push button experiment. We push a button and then we get this here, what you see here. This is the ground state. This is the image of a 150 nanometer glass particle in its quantum ground state of motion, sitting at room temperature in our lab in a vacuum chamber. Yeah? So this is what we can do. And now basically this is where we are, and now we need to ask the question, okay, so we have a pure state wave packet prepared. This is now our 3 picometer pure state wave packet, okay, and the particle is 150 nanometer. So now the next step is, now we need to expand somehow and maybe even create superposition. So we have that now, pure state wave packet, okay? And question is, can we get something like that? So can we get larger? And this is something we're working on at the moment without going into any details. We came up with a protocol, we call it the Super Mario protocol. So here Mario is the one who built the first generation of the experiment, and now this is the pumped up version in which we think we know how to generate non-Gaussian states. It's a beautiful idea. Essentially it means we take our wave packet in the harmonic trap, and you switch off the trap, the particle starts to disperse. So you actually delocalize it already. This would maybe already be enough, because now we have a Gaussian delocalization, and then we have an additional interaction here. Essentially we have a pulse that creates a phase grating and then generates fringes in position and momentum, and basically you could pick out now 2 of those fringes then to have a superposition of 2 center of mass states. If you ask now you should ask the question, okay, what about your parameter space? Okay, so because we had these numbers, you see mass delocalization squared times coherence time, and we need to ask the question, how large is that with respect to h bar over g, assuming that we can have a second particle 10 microns away. Okay, well, the answer is it's 10 to the minus 10. Say, wow, but it's 10 orders of magnitude, wow, it's huge. Oh, this is great, because this is a 100 nanometer particle, okay? And it's only 5 orders of magnitude, and it's actually mass, 10 orders of magnitude, and it's mass square. So we only need 5 orders of magnitude in mass, okay? Which, if going from a 100 nanometer particle to a 5 micron particle, already does the job. Okay, because, r cubed. So here's the 100 micron particle. This is now the superconducting sphere. We trap a superconducting sphere in a magnetic field, anti-Helmholtz coil configuration. And now what we're trying to do eventually is to now generate quantum states of motion of that superconducting sphere. This would be the next step. Okay, so this would solve the mass problem, and then you would already be in a regime where our wanted parameter is larger than 1. Okay, that's it. So this is where we are at the moment. What we are trying to do right now is we try to address these two questions. How small can we make a gravitational source mass in gravity experiments, and how close can we get? And on the other hand, how massive can we make a quantum system and delocalize it very strongly in order to then eventually combine the two. I need to show that because it's important for just making the point. This is the typical FAQs. What we not learn from observing entanglement generated by gravity. Well, let me just read that. The generation of gravitationally induced entanglement is, number one, inconsistent with assuming gravity is described by a classical field theory. Does not tell us anything about the quantization of gravity. Is highly likely, this is what we hope, consistent with a low energy linearized quantum field theory of gravity. Excludes by principle all gravitational collapse models. And eventually, this is but more on the side of the Gedanken experiments, if observed together, let's say with initial space-like separation between the two masses, then there are very strong arguments why this requires quantization of gravity in order to avoid any further conflicts. With that, I thank you very much for your attention, and big thanks to my team for making that happen. Thanks.
Thank you very much. It's just a curiosity from a theoretician, just to have orders of magnitude in mind. Every time that probably theoreticians see a metal sphere coming close to the Faraday shield, we think about like Casimir forces. And I don't know, so I have no idea how is the control of the shield itself. But I mean, first, how Casimir forces compared with the gravitational forces at this level. Mm-hmm. And second, if it's important, wouldn't that actually also generate some kind of entanglement? If you allow this, I mean, the shield wouldn't transfer entanglement between the two masses.
So to the first question, this is an unwanted yet wanted side effect of keeping the distances on the level of a few micron. On that level, you can estimate that Casimir forces still do not become dominant. On the question of transfer of entanglement, the main point of the Faraday shield is that through the generation of mirror charge, and it's true for any electromagnetic interaction, you remove the position-dependent coupling to the other side. Of course, you generate all sorts of second-order effects, right? I mean, if you would sort of be able to bend the shield, but this is exactly now. This is our duty as thorough experimenters to make sure that that doesn't happen. But I agree. Second-order effects will definitely be the ones that you have to be careful about.
The last slide, can you show it?
The one with the people?
No, yeah, exactly. You see, it excludes for gravitational collapse models.
Yes.
How about Yoshi's one? Because in Yoshi, what I understand is like you take it like it's like a sort of a measurement of the position, and then you do something with the outcome. The measurement can be entangled. So people like to mind that you can generate entanglement between the two particles.
So DOC and also the Penrose one, there the decoherence rate scales with the, let's say, non-overlapping mass distribution. Yeah, so the larger you separate, the larger becomes the decoherence rate. Okay, and the point is that the computation that you do is exactly the same than we do, because what they assume is basically that you have self. So it's the wave packet that interacts on itself. Right? So it's sort of a self-localization of the wave packet. But the point is, you see, since the amount of coupling scales with the distance, and we only start in a situation where the two masses are already separated by 10 microns, the delocalization due to those decoherence models would in principle always be much larger, because they would actually already, in preparing the superposition, they would already predict a rate of decoherence in the preparation that is by definition, because the distance is smaller than the ones that we have, larger than the ones we have. So it has to, for those models that exist, Dioschi, Penrose and so on, decoherence has, because the distances are always by their assumption smaller than the ones that we have, the decoherence is always larger. So it has to have already decohered by the time we would actually see coherence. Mm-hmm.
All right. Quick question, Markus. So there is an equation that is a bit new to me, which is nice. The fact that you have some lower bound on the mass.
Yes.
And this has an inverse dependence on the coherence. So what's the trade-off there? Because coherence time is also going to depend on the mass, right?
Oh, we fixed that. We fixed the coherence time. Yes, you're right. So the point is, so if the mass, I did not put the area dependence of the mass there. So this assumes that you fix the coherence time to a certain value. And then, but that also means, of course, that you always have to pick then. So basically, when there's a mass dependence also, there will also be an upper bound on the mass. Okay, then the mass will be bounded both from below and from above. Because for 10 millisecond coherence time, I will not be able to do a Planck mass object. Thank you. Yes. Mm-hmm.
Yeah, thank you. I think we're running out of time. So let's thank Markus again.